Okay. Hello, everyone. Good evening to our colleagues in Singapore, and good morning and good afternoon to those tuning in from other locations around the globe. My name is Ashwin Iyer. I'm from the University of Alberta in Canada, and I and my co-host, Marco Antoniadis from Ryerson University, Canada, would like to welcome you to the second annual APS Masterclass. We are honored that this year's Masterclass speaker is Professor Weng-Cho Chu, Distinguished Professor in the Elmore Family School of Electrical and Computer Engineering at Purdue University, USA. Professor Chu's masterclass today is titled Electromagnetics from Classical to Quantum. Professor Chu received all his degrees from the Massachusetts Institute of Technology. His research interests are in wave physics, specializing in fast algorithms for multiple scattering, imaging, and computational electromagnetics in the last 30 years. His recent research interests are in combining quantum theory with electromagnetics and differential geometry with computational electromagnetics. After MIT, he joined Schlumberger Dahl Research in 1981. In 1985, he joined the University of Illinois at Urbana-Champaign and was then the director of the Electromagnetics Lab from 1995 to 2007. During 2007 to 2005, he was the founding professor, 2005 to 2009, the Y.T. Lowe Chair Professor, and 2013 to 2017, the Fisher Distinguished Professor. During 2007 to 11, he was the Dean of Engineering at the University of Hong Kong. He joined Purdue University in August 2017 as a Distinguished Professor, and he's a Distinguished Visiting Professor at Tsinghua University, China, Hong Kong University, and the National Taiwan University. He's co-authored 3 books, many lecture notes, over 450 journal papers, and over 600 conference papers. He's a fellow of various societies and is also an ISI highly cited author. In 2000, he received the IEEE Graduate Teaching Award. In 2008, he received the IEEE APS Chento Tai Distinguished Educator Award. In 2013, he was elected to the National Academy of Engineering. And in 2015, he received the ACES Computational Electromagnetics Award. In 2017, he received the IEEE Electromagnetics Award. And in 2018, he served as the IEEE APS president. So without further ado, electromagnetics from classical to quantum. Professor Chu, over to you.
Yeah, thank you everybody for joining this master class. I was told to make this class as simple as possible and deal at the undergraduate or senior graduate student level. So the things here are going to be simple. So I hope you wouldn't be disappointed. You're looking for some high-powered stuff. But it's good in the sense that I have to rethink as to how to say many of these things in the simplest fashion. So I'm going to talk about classical to quantum. This has spanned over 150 years of knowledge. So it's impossible to talk about everything. So it'll be like a sampling of many different topics throughout the area. So what I would like to say is that knowledge grows like a tree, and it grows from mathematics and sciences to science-based engineering, then to application-based engineering, and then on to real-world applications and technologies. In the university, we tend to gravitate towards science-based engineering and application-based engineering, whereas in the industry world, you do real-world applications. I like to emphasize that everybody is equally important, just like the human body parts. If we don't work together, we are not going to achieve wonderful things like we have done in the few decades. For instance, we can put 60 billion transistors on the chip, and every one of us carry a cell phone, which has billions of transistors in them. And that is really a wonderful feat of engineering. And I like to think that simplicity is very important. It is very important for us to be able to explain things in the simplest fashion when we talk to our students. So why is the electromagnetics so important? So I would say that Maxwell's equations are one of the most accurate equations in physics. These equations have been validated to a few parts in the billion, and they are also relativistically invariant. if you have studied special relativity at all, it says that Maxwell's equations in one spaceship is the same as that one that is traveling in another spaceship, which is, say, whizzing past close to the speed of light. Okay, and of course we say this is that these equations remain the same in all inertial frame. And also, what is most wonderful that we find in engineering is that Maxwell's equations are valid over a vast length scale, from subatomic dimension to galactic dimensions. And of course, as engineering, we have seen Maxwell's equations being used in nanotechnology. And we also have seen Maxwell's equations in designing antennas for space probes, like the Galileo and so on. So we see the power of Maxwell's equations. And they are also valid over a broad frequency range from static to ultraviolet frequencies. For those of you who are in nanolithography, you know that ultraviolet light is being used at that frequency, which, if I remember, UV of 198 nanometers. Of course, if you're in oil exploration, you work with very, very low frequency electromagnetic field in order for the field to penetrate well into the, let me see, I use a pointer. You need very low frequency in order for the electromagnetic signal to penetrate into the earth. And if you're in computational EM, you would realize that Maxwell's equations are in harmony with differential geometry, which means that you can also study Maxwell's equations with differential forms, which is in agreement with Yang-Mills theory and so on. So because of this wide-ranging power of Maxwell's equations, they have tremendous impact in science and technology. They have impacted electrical engineering, optics, wireless, optical communications, computers, remote sensing, and so on. So I put a slide together like this some 20 years ago, or maybe 30 years ago. When I put those slides, the one that were colored in green were not there. But then just in recent years, if I think about what electromagnetics can impact, there are a lot more things that we can impact now, like nano optics, nano antennas, metamaterials, cosmic force, quantum optics, quantum information, even quantum computers. I think if many of us got into quantum electromagnetics, we will help the design of future generation of quantum computers. So let me give a very brief history of electromagnetics and optics. In the beginning, it was thought that the theory of electricity and magnetism were two different things. And then there were the theories for optics. They were on the right-hand column. So you can see that electricity and magnetism started out with lodestone compasses that the Chinese used many years ago. And also static electricity discovered by the Greeks. But what really spurred the recent development of electromagnetic technology is actually telegraphy. Because of the invention of the voltage cell, people found that you can send pulses of electrical signals along wires. And hence, the age of telegraphy came about. So people like Ampere's, Faraday, Kirchhoff, and of course, Morse in America started to work in this area. And then electrical machinery actually were invented around 1832, which is surprising because this was even before Maxwell's equations were completed in 1865. On the right-hand column, we had the optics, the field of optics, where the Chinese knew about pinhole camera in 400 BC and even lenses. And I guess the Islamic world and the rest of the world knew about the design of lenses to help with the reading of small texts. And of course, in the Western world came about the discovery of Snell's law, and then Huygens and Newton came about with Huygens' principle, and Fresnel did a lot of work, and so did Kirchhoff. Kirchhoff did contributions to both sides of the aisle. And then in 1865, when Maxwell's equations were completed, that they realized that these two columns discoveries were actually one column united by Maxwell's equations. And when they found that Maxwell's equations are really that powerful, many mathematicians jumped on the bandwagon, starting to study Maxwell's equations in great passion, especially like the work of Sommerfeld. He did many work that influenced what I do presently. And of course, there are many unsung heroes among this cluster of mathematicians. Quantum electrodynamics came about around 1920s. And from quantum electrodynamics came what we call quantum optics that we'll talk about later. And electromagnetic technology was developed very rapidly, I would say, before the Second World War and after the Second World War. In the present world, we can do nanofabrication, which is actually an amazing technology if you come to think about it. We can measure very weak signal down to single photon level. And then because of that, we can have nano optics and quantum optics because of our ability to measure signals and ability to fabricate things that are very small compared to even optical wavelengths. And in the 1980s, as I would explain to you later, came the age of quantum information. And this brings about the age of quantum information science. I believe that if we all know quantum electromagnetics well, we're going to make this a very important field in the future. So these were the early days, telegraphies, Morse code, voltaic power, and so on. And it was because of them that gave the birth to the first few set of emerging electromagnetic technology. What is most notable was that shortly after the completion of Maxwell's equations, there was a cable that ran from America to the old world. And then shortly after, a Queen of England, I don't know which queen now, probably Queen Victoria, he heralded in the cable signal or telegraphy signal from England all the way to India, Singapore, and Hong Kong. Okay, and of course in 1894, Marconi as well as Tesla demonstrated that it is possible to send signals using wireless telegraphy. Okay, here is just a very simple picture of that. Even though Maxwell's equations, the way they look are very simple, actually buried in them are actually three regimes of physics. You're in the circuit physics regime if the wavelength of the electromagnetic signal is very large compared to the size of the structure. And then you're in the wave physics regime when the size of the structure is on the order of wavelengths. And here is a simulation of Yagi-Uda antenna, which was invented in 1926. But most amazing thing about this invention is that Yagi and Uda did this invention without computer simulation. They used their physical insight and came up with this design where the front part of the array acts like a waveguide, the rear part of the array acts like a reflector, so signals are just been guided forward. And these were some of the computer simulations did by my students in the 1990s. And of course, if you go to the other regime, when the wavelengths of the electromagnetic wave is very much smaller than the structure, you can think of electromagnetic waves as like particles and bullets. And you can use ray theory to understand much of the physics of electromagnetics in the high frequency regime. So as I said before, I like to focus on one technology that has been impacted by electromagnetics in recent years. This is actually the microchip technology. Even though electromagnetics is not everything, it plays a very important role in the design of the microchips. And what is amazing is that the Moore's law, and many people had spelled as doom even when I first joined Illinois around 2005 or so. Actually, I joined Illinois around 1985, okay? So even then, people were spelling the doom of Moore's law, that it has to come to an end. But it never came to an end, actually, because of engineering ingenuity. And it keeps doubling every 18 months or so, and up to very recent years. It is because of the self-fulfilling prophecy of Moore's. Because if you're a big boss in the company and you say that you want this law being upheld, the engineers have no choice. You work very hard and they're very ingenious and very creative. You keep making Moore's law a reality. And so what has happened in the past few decades has been engineering ingenuity, which means that they have made more use of the 3D dimension of space to design the microchip. Things are done with through silicon bells and different kinds of things to make building the chip almost like building a city, a skyscraper in the city, so that the spaces are properly used of. And what is important is that 95% of chip design is actually done by simulation. With both circuit theory and EM theory, this we call virtual prototyping. And it's only after that is done that the engineers have what they call a tape out session. Then they will tape out the design and send the design to the foundry. Okay, so if you look at some of these things, in the beginning, it was just something looking like that on the left-hand side. But now you have more things looking like this. Okay, you can see that the transistors is at the bottom, and then there are these X and Y lines that takes the signals out, and X and Y lines are more looking like this. And recently we have this FinFET, which stands for field effect transistors. Fin just stands for the fact that they are made very, very small. Okay, so they can make these FinFETs as small as 2 nanometer, which is smaller than the strand of a DNA. To put things in proper perspective, our hair is about 70 micrometer, whereas 1 micrometer is about 1,000 nanometers. And to put things in proper perspective again, the virus that has caused the havoc in the present day is about 80 to 100 nanometers. So we are making things much, much smaller than the virus. That is really amazing, in my opinion. So why does that happen? Well, as I said before, people spelled the doom of Moore's law long ago, but when it comes to overcoming this barrier, engineers are very clever, and they keep upholding the promise of Moore's law until up to very recently due to clever engineering and so on. So I like to go through some very simple examples that we can explain without advanced electromagnetics knowledge. One actually is the fact that we can shield out electromagnetic signals using a Faraday cage. If you put yourself inside a Faraday cage, and if this Faraday cage has been grounded, if somebody threatens you with the electromagnetic gun, you are very well protected. Why is that so? Well, because the moment that the electromagnetic offending source is trying to attack you, a set of charges of opposite polarity would surge into this cage to cancel the field from the other one. Okay, I like to think of this as being that there are little holes on the wall of this cage. Both those holes are very small compared to the wavelengths of the photons. Everything is grounded in photons, as you will learn later on. And when these holes are very small, they are actually in the cut-off mode of these photons, which have very, very large wavelengths. They cannot go inside this cage. And all of us had waveguide theory before. If you had analyzed these structures, for instance, you can see that these are all the waveguide modes. The wavelength has to be smaller than the dimension of this waveguide before it can enter it. Or in other words, you say that approximately photons have a size, and their size are on the order of the wavelength, and they cannot go into something which is much smaller than the wavelength, just like what we learned in waveguide theory. And photons actually ride on the waveform or electromagnetic wave in this case. So photons and electromagnetic fields coexist like between a snail and the house that the snail carries around. This snail cannot enter something that is much smaller than the house that he's carrying. The same for photons, I would say. Well, another thing that we think we can understand very easily is actually magnetic levitation. Okay, magnetic levitation, because you can think of the fact that if you have a superconducting magnet over here, and if you put it next to another permanent magnet, what happens is that eddy current is immediately induced in the superconducting magnet. And in order to conserve energy, the magnetic dipole that has been induced has to be of the opposite polarity from the magnetic dipole of the permanent magnet. So they have to be in opposite polarity to conserve energy. And these two magnetic dipoles repel each other, just like two magnetic monopoles will repel each other. And hence you can see that this small superconductor will levitate itself. And of course, you can see levitations of all kinds in this world. For instance, you can see some street artists who levitate themselves like this picture over here. But the figure on the left-hand side is fake. The one on the right-hand side is real. If you go to a science museum, you can ask for this kind of demo if you want to. Okay, so we have seen all manners of antennas throughout our ages, because we actually are very, very blessed to be living through ages where we have switched from very old-fashioned antennas. I'm sure that if you're a young fellow in the audience, you might not even have seen this kind of antennas, but if you're an old folk like me, you will have seen this kind of antennas in use on rooftops as well as on top of televisions. Okay, but they have been made obsolete by another electromagnetic technology, which is optical fiber. Most homes have optical fibers leading up to the curbside, so they don't need this kind of low bandwidth old-fashioned antennas anymore. And of course, it has also been very important for our communities to study these kind of things, as you can see from this picture over here. Well, I was having a video playing here, but apparently it doesn't play. Okay, but let me skip that video play. And one of the antennas or antenna technology that has remained with us is actually reflector antenna technology, despite leaps and bounds progress in other kinds of electromagnetic technology. We still rely on them because they have extremely high directivity. They're extremely good for communication with signals from outer space. For instance, we have something which is the Arecibo antenna in Puerto Rico, South of America. And then we have a recent one, FAST, in China. They all are built to pick up very, very weak signals, and only with this kind of technology can we have extremely high directivity and ability to measure very weak signals. And then another field that has stayed with us for so long is actually remote sensing. Remote sensing has two kinds, one of which is the active remote sensing, where you send out a signal to have it bounce off the target and then measure the reflected signal and then communicate with the Earth-bound satellite. And then another one is actually a satellite that flies around the Earth and just looking for passive electromagnetic radiation from the Earth's surface. Whenever a body is hot, it emits microwave or electromagnetic radiation, as we can see in this picture over here. The hot body will emit radiation from very low frequency up to very high frequency. So microwave remote sensing is very important, is because it allows us to see through cloud covers. Even in a very cloudy days, if you just use optical remote sensing, you will not see beautiful features like this. Okay, but microwave remote sensing would allow you to do that. And because of the relation to black body radiation, you can actually ascribe some kind of a temperature with the emitting surface. Okay, and here are the people who have worked in this area. And what is to be noted is that one of the persons who work in this area, Hasselmann, was awarded the Nobel Prize this year for his work on studying climate change and so on. Okay, his name is Hasselmann. Well, one of the things that have stayed with us and impacted us a great deal is our cell phone. Okay, it started with Marconi, who demonstrated wireless communication. But what is more amazing is that cell phones are getting smaller and smaller. And every one of us carry one of these in a pocket, and it has a few billion transistors in them. And one of the challenging things about designing a structure like this is electromagnetic compatibility and electromagnetic interference, because you can design the cell phones component by component, and you make sure that each one is working perfect. But when you put the technology together, they start to interfere with each other. And that has always been a headache to antenna engineers or cell phone designers. So I like to take a slight departure and talk about something more mathematical, which is reciprocity theorem. And I find this theorem very meaningful and beautiful. And it reflects also on the human behavior, that we don't impose onto others that we don't like others to do unto ourselves. Okay, Confucius espoused this thinking over 2,000 years ago, I would say. So you could also find this in the Bible. Okay, the Bible also espouses this way of thinking, but unfortunately, most of us in the modern world do not abide by this thinking. And this reciprocity theorem also exists in electromagnetic theory. You can start out with Maxwell's equations and assume that you have two kinds of sources, magnetic as well as electric. And then you can assume that the medium is rather complicated. And after a hard day's work, and if you were to, say, communicate between two antennas, a source antenna and receiving antenna, you can come up with a kind of impedance matrix that describes this interaction. And most of us know circuit theory. And reciprocity requires that Z12 equals Z21. Okay, this is a wonderful theorem. It says if I cannot hear you, you should not be able to hear me. If I cannot talk to you, you cannot talk to me. This is very important in communications. Okay, so if I have an antenna tower here, and if I somewhere in the valley here trying to receive your signal, if I cannot receive your signal, I should not be able to send you the signal too. And this theory is true irrespective of how complicated the environment is. It can be your circuit board, it can be a terrain, or it can be in the optical regime where you go snorkel, scuba diving or doing snorkeling. And you can sometimes look up in the sky and see a picture like this. Whatever the guy on land, if he cannot see you, you cannot see him. Okay, that is what reciprocity says in the simplest sense. So I like to go a little bit mathematical, since some of us like mathematics. Say we like to prove reciprocity theorem. Reciprocity theorem is usually proved with the suggesting of two experiments. One experiment where you turn on sources J1 and M1 and measure the field E1 and H1. The second experiment, you switch off the first set of sources, turn on the sources J2 and M2, and it produces E2 and H2, and you measure them, okay, according to the law of Maxwell's equations. So at the end of the day, after you have done all the complicated derivations, what you can show is that E2, J1, H2, M1 equals to what is on the right-hand side. This is what we call the reaction. This is the field from experiment 2 reacting with the source from experiment 1 and so on. And this is the opposite reaction. Okay, if you kick me in the butt, I should also be able to kick you in the butt. Okay, so this inner product is defined in this manner. Okay, and if you look at the definition of this inner product, if you were to have to implement this inner product on a computer, you would divide space into tiny volumes and make this into a discrete summation. And if this inner product is made into a discrete summation, you have to pick points in all of space to implement this inner product. And you can see that this inner product looks very much like inner product between two vectors, okay? So inner products defined in what we call the infinite dimensional Hilbert space on the left-hand side is very similar to the inner product we have in linear algebra. So let me prove reciprocity theorem in a very simple fashion, that I can rewrite Maxwell's equations, the two that I have written down earlier, into one common equation, such as this one over here, putting all the sources on the left-hand side, the unknowns are on the left-hand side, and so on. And I can rewrite this curl operator in this manner, and hence write this equation as a linear operator operating on the unknown E and H with the known quantity on the right-hand side. So this is very similar to linear algebra. I have made these equations homomorphic to the linear algebra equation, AX equals B, where A represents this L operator, which is a combination of these two. And so I like to alert you to the fact that we seldom think like this, but a function is actually a vector. You will think that, well, E is a three-vector or three-dimensional electromagnetic vector, but it is also a function. A function is also a vector. So we should think of E being a vector in a higher dimensional space. For instance, if I have a function in one dimension, if I were to store this function in the computer, I will have to sample it and then store the sample value. So this, to a computer scientist, looks very much like a vector, okay? So it's a lot easier for a computer scientist to think that the function is a vector. So I like to think, or let you think, that a function can be sampled, and once it's sampled, it's no different from a vector. And that would also happen to higher dimensional functions in 2 dimensions and 3 dimensions. Once you have sampled the function, it behaves like a vector. And once you have these stored values, you can always interpolate in between them to get the more precise value of the function using either one-dimensional interpolator, what we call the head function or the chapeau function. And then we can use pyramid function in 2 dimensions and then tetrahedron functions in 3 dimensions. Okay, so what I want to alert to the fact that this E, which is a three-component vector, which is also a functional space, is actually a humongous vector, just like what I have defined before. And what I have is that this equation is homomorphic. I like to use the term homomorphic, which means that it is of the same structure as this matrix equation I have on the right-hand side. So if I do 2 experiments, one with source 1, the other one with source 2, and then I measure the field in experiment 1 and the experiment 2, and the 2 experiments can be written as matrix equations such as this 2. And then if I decide to inner product the first equation with x2 transpose and x1 transpose, and if I can prove that A is a symmetric matrix, which you can actually do for electromagnetics, you can see that the left-hand side of these two are equal to each other. If you know your matrix algebra well, you can take the transpose of this, it becomes this one, which means that these two must be equal, which means that if I have the field inner product with the source, it should be the same as the one from experiment 2 versus experiment 1 and so on. And written out in its full glory, as in most electromagnetic textbooks, it will be expressed in this way. But actually, at a deeper level, it's just the fact that you have a symmetric matrix system, then we have reciprocity. The inner product here is very similar to the inner product in linear algebra. Okay, so I like to use the remaining time I have to talk about something very interesting, which is quantum electromagnetics and quantum optics. The most important thing is that this has just recently emerged, and I like to emphasize as to why it is very important, because the leaps and bounds progress of quantum technologies, almost on a daily basis, you hear of something making advancement in quantum computers or maybe quantum communication. The holy grail here seems to be quantum computers. Quantum communications have been implemented quite a while back, And we are still working very hard to get quantum parallelism. Okay, quantum sensing is another area that hugely impact our area, because our area has been impacted by remote sensing, biomedical sensing, and all kinds of sensing modality. And if we can use quantum technology to enhance the sensitivity, that will be wonderful. And when we can achieve this, we say we have quantum advantage. And quantum advantage is going to give rise to transformative technologies. Okay, so what I like to say is that quantum Maxwell's equations look very similar to classical Maxwell's equations. They look almost like this. The only difference is that all the observables, all the things that are usually measurable in the lab, have to be elevated to become operators, or they have to be elevated to become quantum operators. Quantum operators do not have meaning until they act on the vector. And in direct notation, the vector is denoted as such. Okay, so in addition to giving these equations the blessing of them looking very much like the classical equation, we have to give them a quantum state vector to act on. Okay, because these equations have to be described by a quantum state. We call this the quantum state equation, very much similar to if you have control theories. This is very much like the state equation in control theory. And each hat here is a constant. It cannot be changing with time. And in control theory, if you have a vector, a matrix operator, then this equation, you can solve that equation in closed form. This is called a time evolution operator. And all the states of the quantum system have to evolve according to this time evolution operator. And in order for you to understand what quantum electromagnetics is, I'd like to start with the theory of a very simple pendulum, a simple harmonic oscillator. A simple harmonic oscillator is actually a simple pendulum. If you linearize this pendulum, it will be very simple. And then you can also see a very simple pendulum if you have a weight hanging off the wall or something like that. And then you have a very simple harmonic oscillation in electromagnetics all the time. For instance, the electromagnetic field in a cavity, as well as a traveling electromagnetic wave. If you would freeze your thinking a little bit, you'll see an oscillator oscillating back and forth at every location in space. But what is important is that this simple harmonic oscillator can be described by using energy conservation. If I describe the total energy of the system to be the Hamiltonian, which is the kinetic energy plus the potential energy. If you work out the potential energy of a spring, it will look something like this. The kinetic energy, P, is the velocity times the mass. So this is also the kinetic energy. And if you require P and X to vary in tandem, so as to keep H a constant, which is energy conservation, okay, you can easily show that for that to happen, the way that P has to change with time has to be associated with how the Hamiltonian changed with X, and then the way that X changed with time has to be associated with how H changed with P. And from this energy conservation argument, you can easily arrive at the equation of motion for a pendulum, which usually is taught to us using Newton's law. But what I'm saying is that you can derive this just using energy conservation argument alone. Okay, so what Schrödinger did was something very, very creative. He saw that, well, we have Hamilton's equation, which is over here, which says that total kinetic and potential energy must add up to a constant. And Schrödinger was very much motivated by the fact that all particles are also waves at that time. They found that electrons also behave like waves. And the wave number of that wave is proportional to the momentum of the particle, according to this law. And Planck also discovered that energy of photons are quantized, and that energy is given by this. And h bar is called the Planck constant, which is a very small number, some things like 10 to the minus 34 or something. Okay, so Schrodinger took these two hypotheses and rewrote this Hamilton's energy conservation equation in this manner. And he did something very, very creative and a very powerful guessing game. He replaced it with the partial differential equation operator, assuming that this wave function has something of this form. And then if this is a plane wave, okay, if you replace this k squared with that function, you will get k squared back for a plane wave. So instead of the traditional Hamiltonian equations or Hamilton equations, Schrodinger came up with this partial differential equation that describes the wave that is hiding behind the particles. Somehow he knew that there must be some kind of a wave because people have reported on wave-particle duality. And because of that, we can write Schrodinger equation more compactly in this manner, where h hat is actually this operator. It should be described as a Hilbert space operator. And one way of saying is that in order to go from here to here, we have make x a deterministic variable into an operator x hat, and the operator, the scalar number momentum into an operator. And once they are becoming operator, p and x now actually become random variables. They're not deterministic anymore. In order to describe this random variable, you need a probability density function. And it was quite a few years later that Max Born decided that the physical meaning of the amplitude wave square is associated with the probability density function. In other words, the electron is going to be found everywhere in this wave function. And the probability of it being found is proportional to this wave number square. Okay. And fortunately, this equation that we have here can be solved in closed form. It was a piece of cake for the mathematician of that time. They found closed form solution to this because once you do this separation of variables, this 2D equation just becomes 1D equation, and these are solved in terms of Hermite Gaussian polynomials, and they can be made orthogonal. And then the eigenvalues are also known in closed form. So the energy level that you find in this equation actually has discrete levels, and the spacing between them are exactly h bar omega, which is the photon energy that Planck has found many years ago. So the energy level is that. And you can also look at the ground state, the lowest energy state of this oscillator. It is going to be looking something like this. And then usually these functions, which we call the eigenfunction, is also called the Fock state or the photon number state, are usually denoted as such by the mathematician, denoted by such by the physicists, but in a very terse way, denoted by such among very many physicists these days. Okay, so you can see that what has happened is that the particle, which was deterministic, becomes random. Its position and its momentum are all random, and you do not really know where they are located as the particle moves back and forth. They are described by wave functions, as I mentioned before. This is called the wave-particle duality, and the first column is the classical harmonic oscillator. I like to give the fact that particles are indeterminate before the measurement as a ghost-injured interpretation of what a quantum particle is. Okay, so one of the very important things that you should learn is that once you elevate P and X to become quantum variables, which we call quantum observables, they become random variables. And since they're random variables, they have to be described by a probability density function, which is given like this. And you can write this inner product. We usually call this inner product. You can think abstractly in linear algebra. It is actually just an inner product between two vectors, and you can use direct notation, which I feel a little bit old-fashioned compared to matrix notation. So if you were to find the average location of the particle, you will go through this using probability density function, which is the average location here. You can also rewrite this using matrix algebra notation, because this is just the inner product between two vectors plus a diagonal vector, or you can use Dirac's notation, which is this notation over here. And similarly, as I say, the momentum becomes an operator in the quantum world. In order to find the average of this momentum operator, you go through an operation, something like this, which in Dirac's notation looks something like this, whereas in matrix notation looks something like this. So what is important is that something that is highly deterministic in the classical world becomes sort of random in the quantum world. You can replace the randomness by an uncertainty principle, the spread of a dot. As this dot moves around, it maps out an uncertain sinusoidal function, so to say. So this is even more pronounced in the laboratory. If you are able to measure down to very, very low energy, say in the single photon level, you'll find that whatever measurement that you have in the laboratory, the outcome of the experiment is random or probabilistic. It cannot be measured with great precision, and as you are able to measure down to very low level, as you turn the energy level very low, the experimental outcome becomes noisier and noisier. This is one of the very important artifact of quantum theory on the electromagnetic measurements. Okay, so there's recently an emergence of what is called a quantum information science. I can summarize this quantum information science in one slide. Initially, what happens is that there were two competing schools of thought in quantum theory. As I say, a quantum system has to be defined by a quantum state, and all the observables are defined by quantum operators. Okay, and as we say in the previous slide, you do not know where the pendulum is until you do the measurement. And if you were to do the measurement, you find that the outcome is probabilistic random. Okay, so there were two schools of thought, and one school says that the quantum state is not known until after the measurement. That means you do not know where the pendulum is until you have done the measurement. Okay, this was promulgated by Niels Bohr of the Copenhagen School. And then there was another school of thought which says that this cannot be true. God does not play dice with us. Okay, there must be something hidden somewhere that is not known to us. So Einstein promulgated the thinking that there was a hidden variable involved. The random nature of the experimental outcome that we see on the quantum level is due to this hidden variable. It is a random variable, so the outcome is still random, but it cannot be such that we do not know where the pendulum is before the measurement. Okay, so this is a very important distinguishing feature between these two schools of thought. And you can actually cook up mathematical expressions and experimental outcome or experiment setting in optics or in quantum optics. And in 1982, Alan Aspect confirmed the correctness of Niels Bohr's thinking that you do not know what a quantum state is before the measurement. To me, this is actually philosophically very important. And it says that your karma is not written on your forehead when you were born. Okay, your future is in your own hands, is what this quantum theory says. So what it says is that quantum information can be hidden incognito in a quantum system before the measurement, because you do not know what the system and what state it is in. You do not know where the pendulum is located before you do the measurement. Okay, and if you can get all these quantum states to work in parallel before the measurement, they give rise to quantum parallelism. I like to give this the ghost and angel interpretation, in the sense that if you have a pendulum or a quantum state, the quantum state can be in the linear superposition of states, such as these ghosts in the room or angels in the room. You do not know where the angels and the ghosts are before you catch them. And once you catch the ghost or the angel, you know where it is. Just like if you were to perform a quantum measurement on this quantum pendulum. We do not know what it is or where it is until after the measurement. Okay? And if we can get all these things to work in parallel, we can get quantum parallelism. This is what computer scientists are trying to do. If you can get all these angels and ghosts to work for you in parallel, you can make the computer super, super fast. Okay. So in conclusion, I would like to say that I explained why electromagnetics has this enduring legacy for over 150 years. I gave the impact history and some simple physics of electromagnetics. I took some examples from textbooks and tried to rewrite them in my own language so that it is easy to understand. I gave a new look of the reciprocity theorem. It's nothing but very deep down is due to the symmetry of the matrix operators that we are dealing with. Okay, so I give a very simple overview of quantum electromagnetics and quantum optics, and we can grow this field. And as you know, all the things that we do in quantum computers are mitigated by photons. Actually, in the present quantum computers that have emerged all around the world, they are dealing with microwave photons. Microwave photons are very weak because each packet of energy is proportional to h bar omega. As I say, h bar is a very small number. So it's extremely difficult to do these things in microwave. Okay, I think if more of us can work together to help build this quantum computer, we will see tremendous speed up in a computer. And one of the things you probably have heard is that it takes thousands of watts to run a supercomputer, whereas it takes only maybe 20 watts to run the human brain. So in my opinion, we will never replace humankind with robots. Okay, there are, of course, these science fiction stories that says that, well, one day the robots will be running around rampantly and they will take over this world. It will never happen because of this disparate nature between how we use energy and how the present day computers use energy. And I hope that electromagnetics will grow more interdisciplinary as you look into this thing in the future, and more of us can participate in this exciting area of growth, I hope. Okay, I'll stop here.
Thank you very much.
Any questions?
Thank you very much, Professor Chu. Very inspiring how you managed to cover such a broad area in such a concise and engaging fashion. I especially enjoyed the discussion on reciprocity. So now the floor is open for questions from the audience. So you can use the reactions option in Zoom to raise your hand, or you can unmute yourself, or you can type your questions into the chat, and Marco and I will moderate them. Marco, we have I have a question directed here to Professor Chu. Back on the earlier slides, Professor Chu said the size of the photon is proportional to its wavelength. Are there experiments that proved this? Is the question.
Well, may I know who asked the question?
The attendee's label only says iPhone, so I'm not sure.
Oh, iPhone, okay. Well, there are no experiments that prove this, I would say. It's just my conjecture from everyday experimental observation, the fact that if the wavelengths that the photon has to write on the waveform, if the wave that the photon writes on is a wave that has very long wavelengths, it cannot enter small structures. I think all of us has this experience before. If you tune yourself to AM radio and happily listening to AM radio when you drive around, and the moment you enter a garage that is too small for the radio wave to enter, your radio will be cut off. Okay, I don't have a proof that this is so, but the mathematics says that a photon has to write on the waveform. The waveform is the electromagnetic waveform. And if the waveform cannot enter the space that the photon wants to go, the photon cannot go to that space, very much like the snail and the house that he's carrying around.
Thank you. We have another question here from Shambu.
Yes. Thank you, Professor Chu, for a very wonderful talk. I mean, it was very insightful. I noted that you mentioned EMC, EMI challenges at the quantum level. I was very curious too, because I myself work in that aspect, not at that quantum level, but at the system level or PCB level. I was very interested if you could put more lights, what challenges we could have to solve in terms of EMC, EMI at the quantum technology. Or
Well, I would say that quantum Maxwell's equations are more richly endowed. Okay, if I look at quantum Maxwell's equations, can you see my screen?
Yes.
Okay, if you look at quantum Maxwell's equations, they're more richly endowed compared to classical Maxwell's equations. Each head here is an operator. You can think of it as like an infinite dimensional matrix operator. We have not used the full power of quantum Maxwell's equations, in my opinion, in our modern day technology. And if you can do that, then we can bury more information in the electromagnetic field, maybe do engineering with it. But that would mean that you have to be able to measure electromagnetic signal in the single particle level, which in this case is a photon. H bar omega is very small. And I think there might be ways to measure very weak photons that we have not discovered yet. But the present way to measure very weak photon is to use cryogenics, cool the room down, so that there are no other interference coming from the environment. There's no thermal photons corrupting your measurement, and hence you pick up the microwave photons. But that might not be the only way. And if engineers are clever enough, we might come up with ways of measuring photons at the microwave level, or even in the radio wave level. Nobody has explored those possibilities. Then whatever you can extract in EMI, EMC, just using a classical signal, will be richly endowed with multi-dimensional signals. But these are challenges that we have to overcome as engineers in order to use this technology.
Thank you.
We are not there yet, but I think if we can work towards the goal, that would be wonderful.
Thanks a lot.
Thank you. We have one more question from the chat that says, sir, when we say Maxwell's equations validated to a few parts in a trillion, what do we actually mean by that?
Well, those are actually validations done by physicists. I'm not very familiar with that because there was something called the magnetic dipole moment or something like that in physics, that every electron has a magnetic dipole moment, and that dipole moment is affected by interactions at the quantum level down to the atomic level, subatomic level. And physicists can measure the size of that constant. And physicists can also calculate that constant using quantum electrodynamic theory. They go through very complicated calculations, most of which I do not understand. They do Feynman diagrams and particle interactions, and they keep how many terms in the interaction. I think one Japanese group recently has kept a huge number of terms and calculated a constant to great precision. And then somebody goes to the lab and measure them again. And then they found that those constants should be in good agreement. One, of course, is based on quantum electrodynamics. Quantum electrodynamics uses Maxwell's equations. Okay, so in a sense, it indirectly validates Maxwell's equations down to a very, very high precision.
Okay, thank you.
You really have to talk to a high energy physicist to fully understand this. I don't fully understand it, but only know the gist of it.
Okay.
Thank you.
Sounds good. We have to find a physicist then.
Yep.
So Professor Chu, our next question comes from Vila Tiukuvara. Vila, please unmute yourself and go ahead.
All right, yeah, thank you. Thank you. I think that talk was very interesting. One thing I didn't quite understand was the quantum parallelism. Could you just like elaborate on how that works, or maybe give an example or how that could be used in practice? It kind of sounds like you like multiple like computations could be done with it at once.
Yeah, it seems that the quantum parallelism hinges on the fact that before you do the measurement, you do not know what the quantum system and what state it is in. It is in the linear superposition of states. Okay, I can think of these states as different ghosts or different angels. The quantum state is in a linear superposition of different quantum states. And if you can program your quantum computer and get these angels and ghosts to dance or to choreograph them so that they can do useful work for you, which is what they have done in China, for instance. There's this boson sampler. It's a very simple computer. It cannot do anything very intelligent. But what it can do is quantum parallelism. It tries to seek the optimal solution to a problem by solving them in parallel instead of using just one path. Okay, you can use a linear superposition of states to explore different paths in this boson sampler problem, and hence arrive at a solution a lot faster than if you were to program a digital computer. A digital computer, you have to program every path. A quantum computer, you can let the signal go through the system just once. I would like to liken a quantum computer very much to an analog computer. I was working for the oil industry, and when the problem gets too difficult to solve, we program an analog computer to solve the problem. The quantum computer, in my opinion, at this stage, is very much like an analog computer. It can only do certain limited tasks, like the boson sampler that the Chinese have designed. It can only do one task, okay, which is to do the boson sampling. And in the future, if we can make computers programmable, which is what many people are trying to work on, we will have more and more powerful quantum computers, or more and more powerful, quantum parallelism and so on.
Right on. Is there, what group is the from China that did the boson sampling? If I could look them up.
You look under Jianwei Pan, J.W. Pan, P-A-N. They are from the University of Electronic Science, China, in Hefei. And recently, just another paper emerged from Alibaba Research Group. And they claim that they can do something much better than the rest of the world. Of course, in America, we have Google, and many companies are participating in building quantum computers. But unfortunately, many of the quantum computers that have been built do not display quantum parallelism.
Right.
When you do not display quantum parallelism, it's no better than hiring a good computer program to rewrite your code. You can get 10% speed up, 20% speed up, maybe even 50% speed up if you change the programmer from a bad programmer to a good one. But if you can get a quantum parallelism happening, you can get orders of magnitude speed up that cannot be done by a human being.
That's very
and
interesting.
I think one example is FFT. All electrical engineers know about FFT. If you do FFT very naively, it takes n squared time. Okay, that is a dumb engineer doing FFT. If you're clever in programming FFT, you can do it in n log n time. And you can show that if you can get the quantum computer to do FFT, it can do it in log n squared time. N is the number of unknowns, okay, log n squared. So you get rid of the n. So the complexity of finding an FFT is greatly reduced due to quantum parallelism. Okay, in my opinion, it's quantum parallelism that does the job. Okay, so you can actually now FFT huge numbers. And this is something of interest to the defense industry. You say that if you can FFT huge numbers, you can break codes. You can actually, there are certain things in cryptography that I do not know very well, that they are written in terms of factorization of numbers, prime numbers, and so on. And there is an algorithm called a Shor algorithm, SCHOR or SHOR, okay? That says that if you know how to program a quantum computer, you can factorize huge numbers much faster than a classical computer. Okay, there's one way to get the government interested in funding this kind of thing. If you tell them that you can win the war, then they will fund you. Unfortunately, this is the present state of humankind. We only fund things to win wars. We don't fund things that advance technology. I really like the logo of IEEE, which says that IEEE is an organization that advances technology for humanity, not for warfare. Okay, so I think if all of us can think that way, we will have a much better world to live in.
I agree. Thank you.
We have our, Marco, do you want to introduce the next question?
Sure. Alex Wong would like to ask a question. Alex, go ahead.
Okay.
Okay. Hello. Yeah, thanks, Professor Chiu, for giving a wonderful talk. It's very nice to see you and very nice to hear of your excellent teaching. You cover so many things in so short time. I want to ask a question off the board as a young faculty myself. And
Where are you at?
I'm in Hong Kong.
Oh, you're in Hong Kong. Okay, I spent 4 years there.
Yes, yes. I actually had lunch with you, but maybe you were one of the. I was one of the many people that you've met with. So
Okay.
it's nice, but unfortunately we can't move around now. But I want to ask this question as a young faculty and maybe for the students. I think we very much like to hear your opinion on what attitude a young academic you think should have. As you alluded to, maybe there are some things, some aspirations we can have regarding where the field is going, but then there are also other forces at play as to maybe where we get money, where we get support. What would be your advice or your perspective on, or maybe from your experience, what sort of a successful academic should have the attitude or should have the approach?
Yeah, I think my number one advice would be that not to isolate yourself. The world is so complicated that everybody has a different view of the world. So if you connect with people from all over the world, you get the different viewpoints of the same problem that you yourself will not be able to see by yourself. So interaction with other peoples from all around the world is very, very, very important so that you can have a multifaceted view of the world, or maybe a fuller view of the world, so that you are not naive, okay? So try to learn from other people, look at other people's view of the same problem, and try to get stimulus, because if you isolate yourself, you would not have enough stimulus to activate your thinking. Whereas if you interact with people from all around the world, you are constantly infused with new ideas, which is very important for a young faculty like this. Okay, unfortunately, we cannot travel anymore, but luckily, God gave us Zoom. So we can still connect by Zoom and talk to each other, okay, without having to travel. But I found that international connections and engagement was very, very important in my growth, for instance, my intellectual growth as I talk to more and more people from different parts of the world and different walks of life. And talk to not only engineers, but also talk to physicists and mathematicians. They will offer you a different viewpoints of the world from their viewpoint. Okay, even talk to chemists and see how they look at the world. Okay, those are important ways to look at the world also.
Sorry, what was the last group of people?
Well, talk to chemists. I mean, when I was young, I hate chemistry and biology.
Oh.
Because you have to
Okay.
memorize things.
Okay.
But you should also talk to them. They have changed our world as well.
It seems like the focus these days is more on interdisciplinary research. So basically, that's what you're suggesting, is to approach others from other areas so that you can broaden your research area.
That's right. I think we shouldn't be stuck in our own cubby hole or up in our own ivory tower, but we should be aware of what other people are doing. And you will be amazed as to how rich the world is if you start to talk to other people. Okay, and that might give you some stimulus on how to improve your technology. Like, for instance, I find that microwave remote sensing is very, very, very important because it can see through cloud covers. And yet measuring a microwave photon is so very, very, very difficult. Okay, so one day we might come up with a technology that can measure microwave photons without cryogenics. Somebody has to come up with these bright ideas. Okay, and then we can have quantum photon-based microwave remote sensing. That would be wonderful. Microwave technology is a lot easier to engineer compared to optical technology because microwave components are about the size of our hands, whereas optical components can be very large or very small. Okay, so a lot of the things are actually built in the microwave regime before they go back to their home regime. Example is the precursor to the laser is the maser.
Right.
Okay, and then there are a few precursors, like people are working very hard on metamaterials. And metamaterials are first validated in the microwave regime. You build all these slot ring antennas and then try to show that you can actually get double negative materials. So a lot more things are easier to validate in the microwave regime. But microwave is clumsy, it's big, components are huge, and we like to get out of it eventually. And getting room temperature technology to work is also very important. For instance, we have this semiconductor laser, which in the beginning needs quite a bit of cryogenics to get it to work. But people were clever. They came up with clever engineering, and they came up with a semiconductor laser that can operate at room temperature. And now semiconductor lasers are everywhere. Okay, so it takes quite a bit of clever engineering to get things to operate at room temperature. And there are many problems out there that you can contribute to.
Thank you.
That's one.
Thank you, Professor.
That is a wonderful way to conclude our second annual APS Masterclass. I would like all of you to join me in thanking Professor Chu for a beautiful overview of electromagnetics, the fundamentals, as well as what the future holds. And it all sounds very, very exciting. So with that, on behalf of myself and my co-host, Professor Marco Antoniadis, thank you very much, Professor Chu. Thank you so much for delivering the talk so early in your time zone. And thank you to everybody who attended. This talk will be available on demand for the duration of the conference and perhaps beyond that as well. So feel free to go back and watch all the exciting portions of that talk at your leisure. Thank you again,
Okay,
Professor
thank you
Chu.
for coming. And
Thank
thank
you,
you for
Professor.
changing time, because otherwise I would have to wake up at 6 a.m. in the morning to give the talk. But luckily you changed it to 8 a.m. You
Yes.
know, which is less unheavenly than the previous one.
Yes, we have the organizers in Singapore to thank for that, because it's in the evening for them now.
Yeah, thank you, Sudong, for changing the time for me. Otherwise, I would have to wake up 6 a.m. in the morning to give this talk.
Yes, yeah. Thank you so much for the wonderful talk.
Okay, I hope it's
Thank you.
useful.
Definitely. I'm sure that this will be very well subscribed on the on-demand platform as well. Thank you again, Professor Chu, and
Okay,
good
thank
night
you
to
for
everyone
coming
in
and-
Singapore.
Thank you.
And thank you.
Thank
Yeah.
you.
Have a good evening.
Bye-bye.
You too.
Have a good day.